In this example, we'll look at a related rate problem that has to do with the draining of a tank. The tank is shaped like a cone, with the vertex of the cone being downward and the circular end of the base of the cone being upward. The tank is 24 inches from the vertex up to the center of the circular base of the cone, and the circular base of the cone is 10 feet in radius. All right. And water is flowing out of this cone at a rate of 20 cubic feet per minute. And at one point, the depth is 16 feet. The depth of the water is 16 feet. And we're asked, how fast is the depth going down? How fast is the depth decreasing? Okay, now, in order to think about this, well, one thing that you have to be careful that a lot of students mistake, there sort of are two cones here. There's the conical tank, the cone-shaped tank, and then there's the cone-shaped water that's in the tank. And the conical tank is not changing. All right, that's when the water is gone, the tank will still be there. But the amount of the water in the tank is changing, and the dimensions of this cone that's made up of the water, all right, is changing. So notice, since the water is drained out of the tank, that involves volume. So we'll need the volume of a cone. And if you check, the volume of a cone is given by 1/3 pi r squared h. So this looks like the cone has two separate variables, but the variables are tied together because the cone of water in this tank, all right, that's changing in size, all right, it has to follow the shape of the cone-shaped tank. And so if we look at this, all right, we can use triangles, and there's a triangle that one vertical leg attaches the vertex of the cone to the center of the surface of the water in the tank, and then that center surface of the water out to the edge, and that's the radius, and that's one right triangle. Okay, then there's another right triangle, all right, that attaches connects the vertex to the center of the top of the cone, or the base of the cone, the circular base of the cone, and then the base of the cone out to the edge, and then back down to the vertex. All right, this bigger right triangle, these two right triangles, by the way, are similar, so their sides are in proportion. This bigger right triangle, the height is 24 foot, the vertical leg is 24 foot long, the horizontal leg is a radius, so it's 10 feet. And the R and H have to be in proportion. So you see, what I could do is I could use that relationship between R and H, that they have to be proportional to the sides of the big triangle. I could use that to eliminate one of the variables. Which variable should we eliminate, R or H? Well, we're asked about how fast the height is changing. The depth of the water is going to be the height of the cone. It's going to be H in this figure. And so we probably should eliminate R and keep H. So what that's going to mean is, let's take this relationship that the vertical leg of the triangle, well, maybe let me say it like this, the horizontal leg of that triangle, R, that's the triangle of the water, all right, over the vertical leg, H, is equal to the horizontal leg of the triangle from the tank, that's not changing, that's 10 feet, divided by the vertical leg of that triangle, which is 24 feet. By the way, the feet cancel here, and this is a height, a distance over distance, or the units should cancel out. And now we have that R is equal to, I'll reduce the 10 over 24 to 12, or excuse me, to 5 over 12, and so we have R is 5 over 12H. Now if we make this substitution, the R will be gone, I'll just have H left. So I'll have V is equal to 1/3 pi times R squared, that's 5 over 12H squared times h. So I just have v and h now in this. So I have, these are the two variables, v and h. Okay, I don't know what v is, but I know that dv dt is negative 20 cubic feet per minute. I believe I have the time correct on that. I'll just double check. It's 20 cubic feet per minute. And h is 16 feet. And we're asked, how fast is h changing? So what's the rate at which h is changing? We're asked about dh dt. Okay? All right, so let's take and look at this. We'll take a derivative. I'll rewrite it a little bit as I'm taking a derivative. A derivative with respect to t. So I have the derivative with respect to t of v is equal to the derivative with respect to t of, now let me put things together. Well, I have a 5 squared, which is 25 pi in the numerator, and a 3 times 12 squared, which is 144 in the denominator, times an h squared times h, that's h to the third. Okay, so I'll be taking the derivative of all of that with respect to t. So when I take the derivative of v with respect to t, I get, of course, dv dt, and I know the value of that, negative 20 cubic feet per minute. And then notice that this is a constant factor, so it can come out, and I'd have 25 pi over 3 times 144 times the derivative with respect to t of h cubed. Notice this is, we have to use a chain rule here because this is a composite function, outside function of cubing and an inside function of h that we're taking derivative with respect to t. So dv dt is going to be equal to, dv dt is going to be equal to 25 pi over 3 times 144, all right, times 3h squared, then times the derivative of the inside function dh dt. Okay, all right, and now we're asked about dh dt, and by the way, I know a few things here. I know dv dt is 20, or I should say negative 20, because the water is coming out, feet cubed per minute. All right, and what I'm going to do is I'm going to solve for dh dt. So I'll invert and multiply, and I'll have times 3 times 144 over 25 times pi. All right, oh, I guess that the 3's could have canceled here, so I can forget about this 3. All right, the 144 over 25 times pi. And then h was 16 feet, so I'll have h squared in the denominator, which would be 16 feet squared in the denominator, is equal to dh dt. And if I calculate all this, this turns out to be a negative 0.143, and let's see, what are my units left? I have feet squared of feet cubed, so just feet per minute is dh dt. So the depth of the water is going down at about 14/100ths of a foot per minute.